Hello everyone, Mr. Fawcett here, and we are about to start our first lesson in our proofs unit. So this is a topic that will come up in almost every unit that we do from here on out. Geometry is a very heavy proof-based course, and a lot of times it can be intimidating to students. But once you get into them, once you understand how they work, once you start to think a different way than you're used to, I think you'll find them fun, and they're quite rewarding once you're able to write out an entire proof by yourself. You really feel a sense of accomplishment because you know that you're doing a lot more work than what you've done in the past. Before we actually get to writing any proofs, I want us to review solving a couple different types of equations. So take some time, solve equations 1 to 4, and then come back and see how you did. Okay, so we're going to start off with equation number 1. I'm going to subtract 15 from both sides. So that's going to give me 3x is equal to 2. Divide both sides by 3, and I get x is equal to 2/3. Now I'm not writing out all the inverse operations. If you don't understand what's going on, just pause the video, listen to what I said, and then you can write out what I said. So when I say divide both sides by 3, well, if you need to write that out on your paper and show that, go ahead. Feel free to do it. You can always pause, rewind, and keep going. We're going to go to number 3, because that's a little easier than 2. We have this fraction on the left-hand side, and to simplify the fraction, to get rid of the denominator, we need to multiply both sides by whatever that denominator is. Make sure you do it to both sides. So those simplify, and I'm left with n plus 8 is equal to negative 30. If I subtract 8 from both sides, I get n is equal to negative 38. I'm going to go to number 4, and again, I'm saving 2 for the end because it is the toughest. I'm going to distribute the 2, so I get 2y minus 10 minus 20 is equal to 0. Simplify the negative 10 and the negative 20, so combine those like terms. I get negative 30. We're going to add 30 to both sides, so I get 2y equals 30. Divide both sides by 2, and I get y is equal to 15. All right, on to the one that looks a little intimidating because we have 2 fractions, but we're good with fractions by now, so it shouldn't pose us too much of a problem. I'm going to rewrite the problem, though, up here to give us a little bit more space to work with. And you should be thinking, okay, I see 2 fractions, I need to add them together. What do I need to do before I add fractions? Well, I got to make sure they have a common denominator. So the common denominator between 3 and 5, the least common denominator would be 15. So I'm going to multiply this fraction by 5 over 5. That's going to get that denominator to 15. I'm going to multiply this fraction by 3 over 3. That's going to get that denominator to 15. I don't have to multiply the other side by anything, because notice that 5 over 5 is equal to 1, and 3 over 3 is equal to 1. And multiplying by 1 is not changing anything, right? So if I multiply one side by 1, I don't have to do it to the other side because the left side's not being changed here. Once I simplify, I get 10t over 15 plus 3t over 15 is equal to 8t plus 3. Combine my fractions now, so I get 13t over 15 is equal to 8t plus 3. I'm now going to multiply both sides by 15. This is now starting to look like equation number 3. That's going to get rid of that denominator, and then I have to multiply this side by 15 as well. So that gives me 13t is equal to 120t, that's 15 times 8, plus 45. Don't forget to distribute the 15 to both terms. I'm then going to subtract 120t from both sides. I am writing this step out. So that's going to give me negative 107t is equal to 45. And then I'm going to divide by 107. So t is equal to 45 divided by negative 107. You can put the negative either in the numerator, the denominator, or just off to the side. Now, we should try to find a common factor to see if we can simplify. Turns out they're not divisible by 2. They're not both divisible by 3. They're not both divisible by 4, by 5, by 15, or by 9. And those are all the factors of 45. So, well, 45 as well. But this is simplified, so our answer is negative 45 107ths. Okay, let's move on. Let's begin to discuss what we're going to need for these proofs. So you're going to solve the following problem on your own, and you're going to write down two things. One, the amount of inverse operations you use to solve. I know you can solve this different ways, so different people may have different answers depending on whether they did more or less steps. And I want you just to write down the types of inverse operations you used. So just the number and then the types, and then we will discuss. Okay, again, this is pretty similar to one of the equations from our do now. We are going to, first I'm going to add 7 to both sides. So that's going to give me 3x plus 6 divided by 4 is equal to 12. So I'm just going to start listing my inverse operations. Divide, sorry, we haven't divided yet. I'm thinking too far ahead. Add 7 to both sides. Okay. Now I'm going to multiply both sides by 4, so I can simplify this fraction. So now I'm going to get 3x plus 6 is equal to 48. So I multiplied both sides by 4. I'm going to bring this up here so we have some more space. And I'm going to subtract 6 from both sides. So I get 3x is equal to 42. So subtract 6 from both sides. And our last step is going to be to divide both sides by 3. And I get x is equal to 14. So divide both sides by 3. Again, you may have done your inverse operations in a slightly different order. I think this was the easiest way, but maybe it was easier for you to multiply both sides by 4 first. You would just have to do some distributing. So let's add up the number of steps or inverse operations. We had add 7 to both sides, multiply both sides by 4, subtract 6 from both sides, and divide both sides by 3. According to my count, that is 4 inverse operations. So we're going to see in a proof, we won't have to specifically write out add 7 to both sides, right? We're going to show that algebraically, but then I'm going to show you some properties or formal names of properties that we can use. So rather than saying add 7 to both sides, there's something called the addition property of equality. And we have similar things for these other inverse operations. So let's look at some of the vocab that we're going to be using throughout the rest of this lesson and unit. Well, throughout the rest of this course. When we are writing an algebraic proof, we need to keep two things in mind. We must show each step. So up above, right, we didn't leave any step out. We showed every step in the solution process. No step is unimportant, right? When you're writing a proof, you have to link every single step together. You can't assume that your audience understands anything. Pretend you're writing it for a elementary schooler who needs to see every step to have a chance at understanding. You're not writing it for a teacher, right? You're not writing it assuming that the person knows how to do it. You're writing it assuming the person doesn't know how to do it, and you're the first one to show them how. So your work has to be clear, it's got to be concise, and it's got to be organized. Number 2, we must justify each step of the solution process. This means that if you perform an algebraic operation, you must describe in words what you are doing, and probably have slightly better penmanship than I do at the moment. So we're going to have 2 columns in our proofs. One is going to be for the actual algebra going on, the stuff that you're used to, right? The other column is going to be for your justifications using words. So let's talk a little bit about what's going to go in the justification column. Well, we have these terms. So we first start off with the addition property of equality, which essentially says if we have an equation, we can add the same thing to both sides, and that keeps the equation balanced. We've been doing this. We just may not have known what the specific property was. But if I start off with an equation, x equals 4, I can add the same thing to both sides. X plus 5 equals 4 plus 5, or equal to 9. And that equation is the same thing. It is still balanced. Nothing's changed because I added the same thing to both sides, right? You know, when we first teach this in algebra, maybe your teacher used a set of scales, right? Where, you know, you have a scale. Let me draw a picture. I'm thinking about showing you with my hands, but you're looking at the screen and not that. So if we had a scale right here, right now it's balanced because there is nothing on each side. If I add the same amount of blocks to both sides, let's say I add 2 blocks to both sides, the scale is still balanced, right? It's the same idea with the equation. If I add or subtract the same thing from both sides, my scale or my equation stays balanced. So just like I said, same thing for subtraction. If I start with that same equation, I could take away 2 from both sides, and my equation is still balanced. Same thing for multiplication. If I start with x equals 4, I can multiply both sides by 5, and my equation stays balanced. Works the same way with division. If I have x equals 4, I could divide both sides by 3, and my equation stays balanced. Now the only thing here is you have to be careful. You just can't divide by 0, right? If I divide by 0, I'm going to get something that's undefined. And you'll talk more about that in upper level math classes, but for now it's good enough to know that you just can't divide by 0. Then we come in, so those were our inverse operations. Those aren't all of them, but they're the ones that we most commonly use. Now we get into some different types of properties, ones that we'll also use when we talk about geometry proofs. So we have the reflexive property of equality. And what this means is that if you have something, if you have a number, if you have a shape, that is always going to be equal or congruent to itself, right? This is kind of the look in the mirror property, right? If you look in the mirror, you're going to see your image. It's going to be the exact same thing. So think, it's called the reflexive property. A lot of times students mess it up and they say the reflective property. But make sure you spell it with an X. It is the reflexive property. All it means is that if you have something like A equals A, you could have 4 equals 4. You could have x equals x. You could have c plus 1 equals c plus 1. These are all reflexive properties, or these all represent the reflexive property of equality. Now, it also works for congruence. So you could switch out the equal sign and swap it for a congruent symbol, and it's still the reflexive property. I know I think I've kind of hammered this home, but if it's the same exact thing on both sides, reflexive property. Symmetric property. The symmetric property is when you want to switch both sides of the equation. So let's say an example of this is when you're solving an equation, right? So let's say you have 9 is equal, let me do a different color so it stands out from what's above. Let's say you have 9 is equal to 3x, right? You divide both sides by 3, you get 3 is equal to x. But maybe you just don't like it written that way because it says 3 equals x and you'd rather have it say x equals 3. Well, you can just flip those around, right? And it means the same thing. This is the exact same as this. It means the same thing. And we can flip back and forth between the two using what we call the symmetric property. And it also works when we have congruency symbols. All right, the transitive property of equality. So if A equals B and B equals C, then A equals C. This may look like the law of syllogism. If you think back to our last section of lessons, when if P implies Q and Q implies R, then P implies R. But now we're just using equals symbols. The way I like to describe this to students is, think about if there's we'll say three professional basketball players, and I'm just going to pick 3 that I think are all pretty good. So let's go with Michael Jordan, Kobe Bryant, and LeBron James. If someone told you LeBron James is as good as Michael Jordan and Michael Jordan is as good as Kobe Bryant, well, what would the relationship be between LeBron James and Kobe Bryant? So if LeBron James and Michael Jordan have the same skill level and Michael Jordan and Kobe Bryant have the same skill level, well, that would tell us that LeBron James and Kobe Bryant must have the same skill level. This is called the transitive property. There's one piece of each equation that links the two together, right? In this case, we have the B. Because that is equal to both A and C, then A has to equal C. Another way you could think about this is using substitution. So if I have, let's say I have the equation x equals 3 and the equation x equals y, well, what's the third equation I could write? There's another equation I could write that's different than these first two, but I have enough information to do so. And of course, I could just say that y equals 3, because y is equal to x and x is equal to 3. Again, the way this works is that I'm just substituting this y in for the x because we know that they're equal to each other. Which leads us into our next property, the substitution property of equality. So if I have an equation, if I know that x is equal to 3, then wherever I see an x, so let's say 9x minus 15 equals 40, we know that I can take this 3 and substitute it in for my x. I can replace the x with a 3 because we know that those two things are equal to each other. So the transitive property is actually a form of substitution. Let me write that. This is a type or form of substitution. And again, we're going to be using these constantly, so you're really going to get a good understanding of all the differences. I know it may be a little hard to parse them out when we're just going through all of them right now, but I want to at least give you that first time exposure. Simplify is, you can use this for your justification when you're combining like terms on the same side of the equal sign. So instance, if you have an equation like 5x plus 3x equals 16, in your proof, your next line could be 8x equals, I said 16, I wrote 18, so we'll just stick with 18. Well, going from this step to this step, all we did was simplify. Another name would be combine like terms. Okay, let's see if we can squeeze one example in. I know we're running a little bit low on time for this video, but it might be nice to get one in. Yeah, so we're going to go a little long for this video, but I want you to at least get some practice before we end here. So look at these two proofs. Just pretend that these are split. These are two separate proofs, okay? We're going to do one of these together, or I know together is not quite accurate because you're listening to a video. But what you may want to do is just listen to what we do for the first one and then try to apply it for the second proof. So I give you the statements. You see the algebra right here. Now we need to come up with reasons for how we went from one statement to the other. The first statement right here, how did we come up with that? Well, it was given to us. Many times, the first reason in your proof is going to be given because you have to start with some information and then you build out from there. So in this case, we were given the equation, then we were asked to prove something over here. Well, okay, our next step. How did we go from statement 1 to statement 2? What inverse operation did we do? Well, we can see that we subtracted 5 from both sides. Right? If we think about this equation, and you don't have to write this on your paper, I'm just showing you. We subtracted 5 from both sides to get the next step. So that is the subtraction POE. POE stands for property of equality. Because there are so many properties of equalities, you are allowed to abbreviate POE. So subtracting from both sides is a subtraction property of equality. Okay, next step. How did we go from statement 2 to statement 3? Well, looks like we divided both sides by 4. So division, property of equality, POE. I think somehow I just turned my pen into a bold font or something. Interesting. Okay, last step. How did we go from statement 3 to statement 4? Well, all we did was switch the equations around, right? We just flipped it. And if you go back up and look at your properties, that is the symmetric property of equality. There it is. That is your first proof that you have completed. So pause the video, take some time, try to do the second proof. You're going to have to reference your properties up above most likely, but see if you can fill in those 4 boxes. Okay, first statement here. Well, let's look at what we were given. So we were given another equation and asked to prove that x is equal to 9. So our first statement was given because we were given the equation. Now, to go from statement 1 to statement 2, looks like we multiplied both sides by 5. So that is the multiplication property of equality. Again, POE stands for property of equality. All right, going from statement 2 to statement 3, looks like we subtracted 7 from both sides, so subtraction property of equality. And then our final step, I think it's pretty clear to see that we divided both sides by 2 to go from statement 3 to statement 4, so division property of equality. Okay, when you come back for video 2, we're going to go through some full proofs. So you're going to have to do both the statements column and the reasons column. Until then, enjoy the rest of your day, and I look forward to seeing you next video.